Let's talk about absolute convergence and versus conditional convergence. If something is absolutely convergent, then no matter how you rearrange the numbers, it will converge to the exact same value. So we have this example here. We have the terms in a certain order, and it converges to 2/3. If you rearrange, then it converges to 2/3. So this is absolutely convergent. No matter how you reorder the terms, it always converges to the same thing. Conditional convergence means that if you rearrange the terms, then the series can converge to a different value. So the alternating harmonic series, if you do not rearrange the terms, it converges to natural log of 2. We could take 1 plus 1/3 minus 1/2 plus 1/5 plus 1/7 minus 1/4, and we could have it converge to something that is not natural log of 2. Matter of fact, if you rearrange in this manner, this one now converges to the natural log of 2 square root of 2. In order to have conditional convergence, it must be an alternating series, though. If the series, the absolute value of a of n, converges, then the original series also converges. So it's absolutely convergent if the absolute value of a sub n converges. This is conditionally convergent if a sub n converges, but the absolute value of a sub n diverges. Determine whether the given alternating series converges or diverges. If it converges, determine whether it's absolutely convergent or conditionally convergent. So let's take the absolute value. Let's look at n equals 1 to infinity of just 1 over the square root of n. So p is equal to 1/2. That is less than 1. So we can say diverges. So this one does not converge absolutely. But now we can go back and use the alternating series test to see if it converges conditionally. So we have the limit as n approaches infinity of 1 over the square root of n is equal to 0. So it passes the nth term test. And 1 over square root of n plus 1 is less than 1 over square root of n. So we can say converges conditionally. Conditionally by alternating series test. Letter B, let's take the absolute value. N equals 1 to infinity of 1 over 3 to the n. R is equal to 1/3. This is geometric. Absolute value of 1/3 is less than 1. So we can say converges absolutely by geometric series. And so now we don't have to go back to the original because we proved that it does converge and it converges absolutely. Determine if the series is absolutely convergent, conditionally convergent, or just plain old divergent. Let's take the absolute value, n equals 1 to infinity. This becomes 1 over n, so we can say diverges by harmonic series. So this does not converge absolutely. So the alternating harmonic series converges conditionally. So converges conditionally by, let's say, alternating harmonic series. Harmonic series. Oh, the next one here. N equals 1 to infinity of 1 over n3 to the n. So let's go limit as n approaches infinity. The absolute value of 1 over n plus 1, 3 to the n plus 1 times n3 to the n over 1. So we have the limit as n approaches infinity, absolute value of the n's go to 1, and there's an extra 3 on the bottom, so that's 1/3. And 1/3 is, oh wait, I guess I did the limit on that. I don't need that. 1/3 is less than 1, so converges Absolutely. Absolutely. By ratio test. Let's look at this one. Let's go n equals 1 to infinity of 1 plus n over n squared. And we're going to go limit. Should we do limit? Let's go, not limit yet. How should we do this one? We're going to go, limit comparison. Yeah, versus n equals 1 to infinity of 1 over n. So this diverges. Diverges by a harmonic series. So we should show limit as n approaches infinity of 1 plus n over n squared times n over 1. So that is equal to 1, which is finite and positive. So we can say diverges. So what we're looking at right here, this one diverges here. So no absolute divergence. So now we're going to say limit as n approaches infinity of 1 plus n over n squared is equal to 0. We're going to let f of x equal 1 plus x over x squared. So f prime of x is equal to bottom times the derivative of top minus top times the derivative of the bottom over the bottom squared. So x squared minus 2x squared is negative x squared. So negative 1 minus x squared over x to the fourth. And we need, well, if you go, there's a couple ways to look at this. Should we try this? Should we go negative 1 is minus x squared is, I need that to be less than 0. Negative x squared greater than 1. So x squared, no, actually, if I add that over, it's still less than. And greater than negative 1. Well, x squared is always greater than negative 1. So now we can say 1 plus n plus 1, or n plus 2, over n plus 1 squared is less than 1 plus n over n squared, always for n greater than or equal to 1. So converges conditionally by alternating series test. For this one, we're just going to write out some of the terms. So if you plug in 1, that's the cosine of pi over, 3 to the first. 1 times 3 to the first. And then plus cosine of 2 pi over 2 times 3 squared. Plus cosine of 3 pi and so on. 2 times 3 to the third. No, 3 times 3 to the third. But that's negative 1, that's positive 1, that's negative 1. So we can rewrite this, n equals 1 to infinity, of negative 1 to the n over n3 to the n. And I think didn't we do one that's almost exactly the same somewhere? Yeah, we just turned it into this one right here. So we're not going to reinvent the wheel. It does converge. Absolutely. So I just wanted to show you that if you're not sure what's going on, you can just rewrite these and they'll reveal themselves. Converges. I think this is absolutely. And by ratio test, but we'll spare you the work for it because we already did that. The Taylor series for a function f about x equals 1 is given by this and converges to f of x. For the absolute value of x minus 1 centered at 1 is less than the radius of convergence. where r is the radius of convergence of the Taylor series. Find the value of r. All right, so we're going to do the ratio test. This is not geometric. Limit as n approaches infinity, absolute value of 2 to the n plus 1 over n plus 1 times x minus 1 to the n, and then times, that's going to be n plus 1. There we go. N over 2 to the n, x minus 1 to the n. So we have the limit as n approaches infinity, absolute value of, there's an extra 2 on top. There's an extra x minus 1 on top. We have n over n plus 1. So limit as n approaches infinity. I guess I can do the limit on this now. Absolute value of 2 times x minus 1 is less than 1. So we have negative 1/2. We divide by 2. Negative 1/2 less than x minus 1 less than 1/2. So the radius, r, radius of convergence, is 1/2. Find the first 3 non-zero terms in the general term of the Taylor series for f prime, the derivative of f about x equals 1. So letter B. Let's get how many? First 3 non-zero. So we should, let's find some, let's go f of x is equal to, when we plug 1 in, we get a positive. So that's 2 over 1. So 2 times x minus 1 when we plug in 1. Then when we plug in 2, that's going to be a minus 2 squared. Let's just go 2 squared over 2, and then x minus 1 squared. And then plus 2 to the third over 3, x minus 1 to the third. There's 1, 2, 3. How about we go one more? Let's see if we'll just go one more anyway. 2 to the fourth over 4, then x minus 1 to the fourth. Plus keep on going. Find the first 3 non-zero terms in the general term of the Taylor series for f prime, the derivative. Okay. All right. F prime of x is equal to 2 minus, when we multiply by 2, that's going to be 4 times x minus 1. Then when we multiply by 3, that's plus 8 x minus 1 squared. And then we multiply by, I guess that's the first 3, isn't it? 1, 2, 3. Find the first 3 in the general term. So plus, the general term is going to be, it's alternating. So negative 1. What if we did to the 0, I suppose? So n, and then 2 to the n plus 1, and x minus 1 to the n. So that seems to be the general term. All right, letter C. The Taylor series for f prime about x equals 1 found in part B is a geometric series. Find the function f prime to which the series converges. Use this function to determine f for all that. So a sub 1 is equal to 2, and the r is equal to negative 2 times x minus 1. So f prime of x, the function, is 2 over 1 plus 2 times x minus 1. And on a free response, I would certainly leave it like this. But if we were looking for the answer on a multiple choice, we could distribute. And the multiple choice answer might be, was it negative 1 plus 2x, something like that. So, but I would leave it like this right here. So, and then here are some answers for it. Curious to see how they left it. Oh, okay, interesting. Down there for, okay, all right. Did they I must have not read this right. Use this function to determine f. Oh, okay, all right. I needed to go to f. All right. So, f of x is equal to the integral. I'm going to kind of cheat here. Yeah, I guess they just have plus c. Oh, where are we getting f of 1 is 0? F of 1 is 0. Let's take a look at that. F of 1. How do we know that? Yeah, okay, that makes sense. Because up here, F of 1, if you have 1 for all these x minus 1s, F of 1 is 0. Okay, that makes sense to me. All right, let's take a look at this one then. We got 2 over negative 1 plus 2x dx. And so f of x is equal to, let's go with natural log of the absolute value of negative 1 plus 2x. And then that's going to be plus c. Now, we'd get the 2 if we took the derivative of this. It'd be 1 over negative 1 plus 2x and then times 2. And we would get that 2 when we took the derivative. So now we're going to use the fact that f of 1 is 0. So 0 equals natural log absolute value of negative 1 plus 2 plus c. So 0 equals natural log of 1 plus c, but that's 0. So c ends up being 0. So f of x is equal to natural log absolute value of negative 1 plus 2x. And are we seeing that on the rubric down here? Let's take a peek real quick all the way down here. Yeah, and then they say for this right here. So 1 for the derivative, 1 for the antiderivative, and 1 for actually reading the instructions thoroughly and getting f of x.